All right, welcome back. Good afternoon. If you remember, we were talking about out of order execution and particularly the advanced topics that we were talking about. So today's plan is we're going to finish this remaining slides for this topic, and then we're going to start a new topic on caches. Is there any questions before we get started? People are busy with their midterms, so hopefully things are going well. So, okay. If you remember a few last things that we were saying last time, one of them was renaming. And I said that one way of renaming is using the RAT and physical registers. Another way of renaming is using a tag system and storing things in the reservation station itself. For that, then you no longer have quote unquote physical registers. You still have your register file, which has your architectural registers. But on top of that, you're going to store the value inside the reservation station as well. And as I said, this is going to be what you will implement in your computer assignments as well. There's also two ways of renaming, the explicit and implicit, which we talked about the differences. The one that we talked about in the class, the renaming algorithm that I went over, was the explicit one, which is on this side. So this one is explicit. But you can also have this, and as I said, this will be what you're going to implement in your computer assignment. Okay. Then we also talked about the wake up. So wake up is when you have an instruction that is dependent to the previous instructions, and that instruction is executed and finished. And now you want to wake this instruction up to feed into the execution unit, right? So there are two ways that you can do this. Excuse me. So you can, if you have a register file here and your reservation station here, this is a read before issue, or this is read before issue case. In that case, your waking up logic and your forwarding logic are both going into the reservation station. This is, again, similar to the examples that we gave you in the class. But, and then this is usually what we call data capture scheduling window, or, okay? The other option is, and by the way, here you also need to update the registers, but this update happens only at the retire stage, right? So you only update the register file at the retirement. Then in the non-data capture scenario, you have your reservation stations here, and then you actually read the values from your register file. In this case, you need to wake up things here. So the wake up happens still happens in the reservation station. For some reason, my voice is cracky today. But your forwarding needs to happen in the register file, right? Because you need to read the values, and the values are the ones that are inside the register files. And if you remember last time, this register file technically is kind of, think about it as like a cube. So this register file is like this. There are actually multiple of these instances of register file going on here, so that whenever you need to do some speculation, you kind of create a copy. And usually we have what we call a clean register file and dirty. So like the top one, you can think about it as a clean, and all of these guys are dirty register files. And when we are sure, then we write the dirty ones into the clean one. So think about these as like checkpoints that you have, and this one is the most is the stable one. So one that doesn't have any speculation with it. Okay. All right. So there is also another thing that we kind of like, the last thing we were talking about last time was the selection logic. So the question is, when is a good time to wake things up, right? Do we wake things up when we are issuing one instruction? Do we wake things up during the execution of an instruction, or do we wake things up when the instruction is completed? Okay. And interestingly, you can actually do all of these things. Of course, the ones that makes more sense and the most intuitive one is when the instruction is completed, you want to wake up the next instruction, right? But if you have a very deep pipeline like this, then what you would do is that you can actually wake things up pretty quickly. So you when you're selecting this instruction, the producer instruction, you also wake up the dependent instruction, the consumer instruction. Since this one actually goes through the pipeline, by the time that it actually reaches to the execution, this instruction is already completed and you can forward it. So you let the read and everything happens, but then you forward. So it's kind of similar to the way that we are forwarding the pipeline, right? You let the instruction go to the decode, go to the execute, and then you forward things from the previous instruction. Yeah. Yes, it has some sort of hazard dependency, and then the previous, now the dependency is resolved, or is going to be resolved. In this case, actual dependency going to be resolved here, but you actually wake it up here. Yeah. Oh well, this is the terminology of the Intel processors, so we didn't talk about it, but yeah, it's kind of like the scheduling has multiple steps, so like you have to read it from the registers. We didn't talk about it particularly in this class. Yeah, but as I said, the more intuitive one is when the execution is finished, then you wake it up, right? So you wake it up and let the instruction go. But as you can see, you like 3 cycles you are kind of wasting, right? So it's like extra 3 cycles that you could have actually used. Now you're wasting with this particular design. So it's as if like you're putting some form of a bubble in this. So you're wasting 3 cycles. But the nice thing about this is that very straightforward, right? That's one thing to note. So going back to the select, the second thing for select is what policy should be used, right? So let's say they have like 4 or 5 instructions that are all of them ready to be selected. Which one should be select? Let's say we only can pick 1 instruction out of 4 instructions. Which one do you think we should select? Any suggestions? Yeah. So you might want to like do the least PC, like the oldest instruction. Okay. Any other suggestion? Yeah. One that has most dependency in future. So you kind of like have a mechanism, see which one helps to kind of unlock future instructions. Okay. Yeah.
I don't know, maybe the tendencies, and it's probably not that it may not be always possible to rearrange the instructions, but maybe to be.
So rearrange instructions to achieve what exactly? So in your reservation station, you rearrange things? Okay. Any other suggestions? Yeah, so usually you can do 2 things. First, you can have your issue queue to be an unordered issue queue. That is the thing that we kind of discussed in the example, that I just don't care about the sequence of instructions or like one after another. What I do is that I scan through the table and I find the first available place available row and put the instruction there. Okay. And I don't reorder anything as well. I just put down instructions as just like, you see the first available seat here in the room, you go and sit there. But the other option would be like, asking everyone to kind of like be reordered, right? The nice thing about this is that this is incredibly simple. It's very easy, very low power overhead. But the problem is that finding instructions become difficult, specifically if I want to flush things off of the reservation station. Then I need to scan through the entire table because each instruction might be anywhere, right? So if I, for example, let's say I have PC equal to 0x100, and this instruction is the branch instruction that needs to be flushed, then I need to find everything that is above 0x100 and need to flush them, right? And if this is an unordered queue, I need to basically check every single row, check the PC and see if the PC is bigger than that value and kick it out or flush it. So that might be not the most efficient if the recovery is required, but in most cases it's very efficient because you can just find the first one, no logic is needed, and so on. The other one that is used, as commonly used, is what we call age order queue. Okay, so age order queue is that, think about this as a table like this that has rows. The first instruction goes here, the second instruction goes here, and so on. Then once I issue this instruction, I collapse the queue. That is, everything will be shifted upward. So this one goes here, this one goes here, this one goes here, and so on and so forth. So we always kind of maintain the age of the instructions. You only put things essentially at the end of this queue. And if I bring something in the middle, then again, I collapse it from the middle. So for example, if the next instruction that I'm going to issue is this instruction, then I will make sure that these instructions are going to be shifted upward. So wherever we pick something, we shift everything below it upwards. This will guarantee that everything will be ordered based on their age, right? And when I say age, keep in mind that age is not necessarily the PC, because, for example, if you have a backward loop, this instruction might be older than this instruction, right? So age and order is not necessarily the same. Like a PC order and age, not necessarily the same thing. That you might have instructions that has higher PC but are older than the previous instructions. So keep that in mind as well, that these are two separate things, okay? What is the downside of this? The downside is, so of course, this is much better in terms of performance, because now you're ready to kind of flush things. You just go through the table and boom, flush things. But every single issue now is more power consuming, because now every single issue also requires for you to shift the entire thing upward. So that would be an additional activities that you need to do. So keep that in mind, that this is an issue to do. Okay. Which one are we using? Different processors use different ones. Many of them are actually using this age order issue model. Some form of aging is usually tracking some form of either dependency, or the age is usually important because you want to maintain some quality for your system. Okay. I already talked about this. When should we wake up, or how soon should we wake up? Once selected, once executed, once committed. And I said that there are two actually different options, which both of them have been used in modern processors. Of course, if you want to get more performance, you want to do this. But if you want to make things simpler, you want to do this. Okay. Another problem with being fast is, so I show you here that here I assumed, so this one is the top one is straightforward and it works all the time, because you only wake things up when you have the data, the instruction completed. So great. This one though has a problem, a big problem. And that problem is that you assume that you for sure have the data ready, right? So you for sure have the execution ready. But what if that data is not ready? And why it's not ready? Because remember I told you that instructions in the execution unit can take multiple cycles, right? So one can take one cycle, one can take 3 cycles and more cycles. Particularly if you remember, I told you that memory is also part of the execution unit. And depending on whether we have data in the register, data in the L1 cache, L2 cache, and so on, the time it takes for this data to be available might be different. Okay. So imagine that, for example, in this case, you're waiting for a load word, and this load word is not finished at this point. And you kind of assume that, oh, okay, this instruction that's waiting for the load word, at this point you want to execute it, right? So that will create a problem, right? Because the data is not available at that point, but you assume that the data is ready, okay? So this is what this is another form of a speculation, right? It's like branch prediction. Remember, in branch prediction, we assume that the data will be like, the path will be taken or not taken. Here we assume that the value will be ready, but it may or may not be. So you take the chance, you take the prediction, you guess that it might be ready, you let it go. But if at this point I see the data is not ready, what should I do? I would do the same thing that I did with my mispredictions. I need to flush that instruction and redo it, okay? So if at this point I see that the data is still not ready, I need to flush this particular instruction from the pipeline. And if there are other dependent instructions in future stage, I need to flush them out as well, okay? So it's form of a speculation, and I make a guess, I feed it into the pipeline, I see that I made a mistake, I need to revert it, okay? So this is what we call speculative scheduling, okay? So the idea is that I don't want to wait for instructions for dependency. If I have independent instructions, of course, I feed them into the pipeline, right? But if I don't have independent instructions, I need to pick something. Either I need to stall the processor and say, okay, everybody waits until that instruction is finished, and then I can feed things into the pipeline. Or I can say that, okay, you know what? I'm going to make a guess and say that, okay, by the time that instruction is finished, I'm going to let this instruction go into the pipeline. But then if I have things such as, cache miss, cached miss, or aliasing between the store and loads, I need to flush the pipeline. I need to flush those instructions, and not just that instruction. There might be also future instructions that I need to flush. Okay. The process of flushing usually is also called squashing. Okay, so you squash the pipeline. Squash and flush is the same concept. So what you would do is that in case of you do speculative scheduling and you saw that your data is not valid at that point that you want to execute them, you need to squash everything between your issue and execute. So everything that you do in the reservation station, between the reservation station and issue, you need to squash them. If the instruction is within the execution unit, you need to squash this as well. Okay. Another interesting thing that we usually do is what we call coloring. Since instructions might be, dependent to each other. So for example, let's say I have a load word. So what I do is that any instruction that is dependent on this load word, I color it red. So let's say I have an add, and then I have another sub, and so on and so forth. There might be instruction in between that is not dependent to that load. Okay, so I will use a different color for them, and so on. There might be actually many different colors in your execution. So colors, think about them as tag, right? So like 0, 0, 0, 1, 1, 0, and so on and so forth. And the way to flush things is that I only flush the relevant color. So for example, if I see that, oh, load is not available, all I need to flush is this one, and this one, right? I don't need to flush the blue ones, or I don't need to flush the green ones, okay? So the way to make things more efficient, remember at the beginning, people were asking that, oh, why are you flushing like I3? Because I3 is even before 4. The way to kind of prevent those kind of unnecessary flushing is that you color the instructions. So dependencies will be colored, and you only find the tags that are relevant to that instruction and only flush those instructions. Okay, same thing for branches. You can also color instructions that are after the branch and color the instructions that are before the branch, and only flush things that are colored with that branch. Make sense? Questions? And usually for the coloring, we use this 1-bit vector, 1 hot bit vectors, right? So like, let's say we have 8 bits, so we do like 1 0 0 0 0 0 0 0. This is one color. 1 0 0 0 0 0 0 0. This is another color, and so on and so forth. How many colors we can support depends on the size of this 1-bit vector. Yes. Squash, it's like similar as flushing. Like flush and squash is the same thing. Yeah.
There were because the perspective of scheduling.
Yes, if our speculative scheduling is wrong, we need to squash. And generally, as I said, squashing and coloring can be also applied to branches. So any speculation, you can apply coloring to it.
And then
Why do you want to? You cannot stall the execution units. That's the problem. So the question is why we cannot stall, because at that point the instruction is already in the execution unit, and also there's like other instructions that are dependent to that instructions that are also inside. So you need to also flush all of them. Yes, a start of issue and end of execution. Yeah. And then, so in our examples, we only have one cycle between them, but as I show you in an example, there might be multiple cycles in between. Yeah.
So even if there's like an instruction and it's not an issue, if that was in the execute, it's
if there is what is
the data is not ready.
Yeah, so if this add is waiting for this load. No, so you only squash, so that's what I'm saying. You usually couple this with coloring. So you only squash things that are colored that way. So if this instruction is dependent on that, let's say, for example, I assign yellow. So I only go to the pipeline and find the yellow ones and squash those. Yeah, load would, of course, you let it finish, right? So load would has to be finished. Otherwise, then you will be an infinite loop. You never finishes. So it's similar to the way that we did the stalling and bubbling, right? So in the stalling, we also said that if this is, you let this instruction continue and then you replace this with the bubble, right? Same story. Okay. So as I said, there is also like, where do we store the operands? And we discussed this. We either store the values in the reservation station and read it from the actual physical register file, or we actually also read the values inside the register file, inside the reservation station. Okay. So the two ways that we are doing this is, with the explicit like read before issue, read after issue. If you want to store the values inside your reservation station, you can. But if you want to store the values after the instruction is being issued, you can also do that. For that, you just need to store the tags or the name of the registers inside your reservation station. And we talked about the pros and cons of each of these approaches. For forwarding is also, as I said, we talked about this as well. When is a good time for forwarding? We can forward things when the instruction is complete. But this means that the ROB design will be more complicated. But you can also make it very simple and say that, okay, I just let we don't do forwarding at all. I'll let the instruction to retire, and I always read the correct value from the register file, right? That makes the design much simpler, but of course, much slower, because there could be one instruction that stays in the ROB for a long time before being retired, and as a result, every instruction needs to wait for this instruction to retire to be executed. So you don't want that to happen. If you want a fast design, you want to forward things as soon as possible. Even like here, as you can see, if I do speculative scheduling, I technically even not forward it when it's completed. I back it up even before the instruction is even completed, right? So you can fully optimize this design if you want to. Okay. And this is the steps for recovering and flushing. As I said, for any sort of speculation, including scheduling a speculation or branch misprediction, you need to do a lot of things. So the flushing is a little bit involved. So the things that you need to do is that you need to flush the wrong instruction from the reservation station. You need to also remove them from the ROB. Even if they're completed, you need to remove them. You need to restore your RAT if you have a RAT. You need to free the destination registers. you need to free the functional units and you need to update the PC. So you need to do all of these steps in your design to make sure that you go back into the stage that you were supposed to be. Okay. In the discussion sections, actually, you're gonna like see an example of this when the branch is being recovered. So you see what are those steps. Yeah.
The original instruction, which is like which is the execute or when it reaches right back within the dependent instruction, like or it's like not right again. Here's that.
So the question is, when exactly are we flushing things? That really depends on the design. Okay, so you can flush things as quick as possible. For example, even in like the dispatch stage, if you have the branch logic there, but it could be also happening during the execute stage. So it really depends on the design of like, and then also depends on what sort of speculation are we flushing from. For example, for this particular scheduling speculation, you can only flush things at this stage here, right? So you don't know it before then. For branches, it's slightly different. And as I said, there are many different speculation happening in the out of order. So any of them could be at any point. Yeah. Question is when the branches are resolved, and as I said, this really depends on the logic. Yeah, you can assume that it could happen during the decode. Usually for modern processors, it happens during the decode. All right, how do we exactly recover these things? Like all of these things, where do we, like, how do we exactly recover? There are typically two ways of doing this. There is this log-based approach that you kind of store the logs. Like, remember you said that, okay, we also store the old destination register. We also store the old PC and so on and so forth. So when we go one by one and recover them, that's one way of doing this. The second way of doing this is what we call a checkpoint base. Checkpoint base is like, okay, I have multiple of tables. I have multiple register file. I have multiple RATs. I have multiple reservation station even, and so on and so forth. Whenever I make a speculation, I take a checkpoint. I copy everything into another registers, another table. And then when I see that I need to flush, all I need to do is copy that back into my table. So it's very quick in terms of recovery because you have the copy of everything and you know that, okay, at this point I need to recover. All you do is just a quick copy, okay? Versus the log base, you need to go through the logs and check one by one and see whether the log is relevant or not and copy it back. Of course, the downside of the checkpoint is that the area overhead is massive, right? So think about, usually this modern processors has up to 8 checkpointing points, which means that you technically, every table that you have in your design is 8 times, okay? And then you have a superscaler, you might actually need to have multiple of that. So your area overhead is massive, but the recovery is very quick because all you need to do is copying one of the type tables back into the other table. You don't need to check anything. You don't need to go through the rows one by one. It's instant, basically. Okay. And then what you need to do is when the instruction deems safe, you discard that checkpoint or discard that log, right? You don't maintain those checkpoints all the time. That's why I'm saying that you usually need, like, let's say up to 8 different checkpoints, because if I have, nested branches, like branch, up to the 8 nested branches I can support, but at some point these branches will resolve, right? So for example, you see that, okay, this branch is resolved. I no longer need to maintain a checkpoint for it because it's no longer speculative. So it's not like I maintain these checkpoints all the time. Once I see that this instruction is no longer speculative, I'll let go of that checkpoint. Yes. Yeah, you need a lot of memory for the checkpointing, right? You need a lot of tables. You need for every table you need n number of tables, right? So depending on how many checkpoints you can support, the storage overhead would be massive. It's also good to look back and summarize how we handle the hazards. So the raw data hazard is supported by looking at the ready bits of our reservation station, right? So whenever the ready bits are not ready, we don't issue that instruction. So that's how we fix the raw data hazards. Control hazards, we have the recovery mechanism for our ROB and RATs. And then structural hazards, we also have ready bits for things like functional units. We have ready like availability. We check the availability of ROB or reservation station. So we essentially, like, whenever they are full, we stall the front end of the processor and so on and so forth. So we have these mechanisms to kind of fix these issues, and the renaming also fix the incorrect hazards or unnecessary hazards, like, right after write or right after read. Okay. Any questions about the hazards? Great. There's also another hazard that unfortunately is created in out of order execution, and that's called memory dependency. So you can also have the same way that you had hazards for registers. So for example, I had an instruction like this, right? So I had x3, x2, x1, and I had like sub x4, x3, and let's say x1. So I have a raw data hazard here, right? I cannot run this instruction before this instruction. And with the reservation station, we can fix this issue, right? But now think about the scenario like this, that I have store x2, I don't know, like 4 and x0. And then I have something like load word x3, 4, and x0, okay? So what is happening is that in this case, the value of x2 should be written to x3, right? So the first one basically says that write x2 into the memory address 4. And this one says read the memory address 4 and write it to x3, right? In other words, I'm saying that x2 should be updating x3. But as you can see, if I let these instructions to be reordered, right? Then if load happens before the store, then the value that x3 will read is going to be an old value. It's going to be a wrong value, right? So similar raw data hazards that we have here happens here as well. But the problem and the challenge here is that for this particular case, it's easy to detect that, okay, these are the same addresses, right? But what if, for example, the first one would have been something like x1, okay? So if I have a scenario like this, do you think we have dependency or not? Who think we don't have dependency? Yeah, the answer is that we don't know. It really depends on the value of x1. If x1 is 0, then we have dependency. If x1 is not 0, then we don't have dependency. So how do we know this? That is a problem that we have with memory dependencies. Okay. We also can have problems with like store and store, right? So if I have two back-to-back stores, I'm going to have the same problem. If this store happens before this store and these stores happens to happen in the same address, again, I'm going to have a problem. So there's going to be these kind of read after write or write after write or write after read problems that we need to fix, okay? And then keep in mind that renaming is not going to fix this issue, because renaming is for registers, it's not for the addresses, okay? So renaming is going to give you the same thing. So I will rename this, for example, to P1, and I rename this to P0 or whatever. You still need to know whether P1 and P0 or P1 and P2 are the same, has the same value. So if you're talking about values, we're not talking about the register names themselves, okay? So renaming is not going to fix that problem. Yes, sir. Yes, this memory hazard arises because of out of order, right? And in order, we didn't have this issue because we always run the the store before the load, right? But here, since I can reorder things, I can also reorder these instructions. And keep in mind that reservation station also cannot catch this, right? Because reservation station in this particular case, it says that, X, for example, if this is X0, this is your RS1 and RS2, right? And RS1 and RS2 might be, both of them might be ready. So, but let's say, for example, in this case, this one is not ready. So you can actually like issue this instruction before this instruction. So it's totally possible with the way that we have instructions in our design that we issue this the second instruction before the first instruction. Okay? So how do we fix this issue? Anyone wants to suggest any solution? This is, by the way, called memory ambiguations because there is an ambiguity on whether or not these things are relevant to each other. Okay? Yes. Track the values. How would you do that? Okay. Okay. Yes. Yes. Yeah, you can also have a temporary buffer, right? So similar ideas. Yes, that's exactly what we do. So in order to fix this issue, we have this thing called store queues, and you're gonna later see load store queues. Okay. So load store queue is like act like an ROB. It actually could be part of the ROB or could be separate unit. That what it does is essentially assign an entry into the store queue during the decode stage. Okay, so whenever I see an instruction, since I'm reading instruction in order, I'm gonna basically put a new entry. I can create a new entry if I see a store word here into this store queue. Okay, so I'm gonna say that, oh, okay, there is a store word here. Okay. Then what will happen is that the value that is going to be written into this store queue is also will be value that whenever this store word instruction is actually executed, I'm going to run this, I'm going to update this value. But the important thing is that whenever there is a load, instruction, right? Or whenever there is another store word instruction, if I want to execute, so there's like a subsequent store word instruction or subsequent load word instruction. Whenever I want to execute these instructions, I put them into this store word table, okay, and I only execute them and write them into the memory when the instruction is retired, okay. Which means that I make sure that all of my stores are actually serialized, right? So what I would do is that I store the temporary values into this store queue, okay? And this store queue makes sure that I only write it to the memory when the instruction is retired. In other words, I make sure that things happens in order when we are writing it to the memory. And if there are future instructions that needs to read this value, what I would do is that instead of going back and read it from the memory, I read it from this store queue. Okay, this is why we call this load store queue. So it looks something like this. The idea is that whenever I want to load something or whenever I want to store something, instead of going to the memory, I will first go to this load store queue and search through that load store queue. If it's there, I'm going to read my value from there. Okay. And if it's not there, that's when I actually go to the data memory and bring it. Okay. This way, it ensures that if I put this instruction when I'm decoding the instruction, so if I put my load and store within when I'm decoding the instruction, if there are any future load, I see that there is actually dependency to the previous one, right? Then I don't issue that instruction, okay? I'll wait for that instruction to finish, and then I forward it. If the value is already available there, I can forward it from here to here. So I can actually forward the future values to the previous values if needed from the forwarding. Yes? So the question is, do you store multiple values? No, so it's usually one per one. So one address and one value. Yeah.
Like the ROB already, like I get this part, but like more consistently about not writing it symmetric until it's tired like this stuff. That was for the ROB.
It's so that's what I'm saying. So for memory, you can have it so store. You can think about load store queue as part of the ROB, but it has additional things. So it can also forward the values to the other instructions, right? So load store queue, think about it as like part of the ROB, but it's particularly kind of like dedicated for the instructions. It can be part of the ROB, but since it's the reason that it's different because then it makes the searching much more efficient, right? For ROB, you need to search through all the instructions, see, okay, so there are some instructions that are not even load and stores, and you need to check them as well. So there needs to be tag systems and all that. Versus a load store queue, you know that, okay, I have a load, you search that address through your load store queue, right? And see if it's a hit there. If it's a hit, you get the value from there. Make sense?
Yeah.
Mm-hmm. Yeah. Once the instruction is retired, then you actually take it from the load store queue and write it to the memory. Yes. Yeah, you flush it this from the ROB. Yeah. Uh-huh. Yeah. You did invalidate it from the LSQ and ROB at the same time. So this will fix these issues, right? So we will fix the write after write and write after read issues if you have something like this, right? But what if we have something like this? That I have an instruction, okay? So I have a load R3 that reads from R6, okay? Then I use R3 to create R7, and I store R7, I store R4 into the address of R7. And then I also have an R1, and I load things from R1, okay? And now think about this, is that if R1 and R7 are not equal to each other, then it doesn't matter when this store happens, right? I can reorder this store wherever I want and whenever I want. But if R1 and R7 is the same, are the same values, then this load definitely needs to happen after this store, okay? But the problem with, so I told you that, okay, load store queues, what I would do is that I put this guy into the LSQ and say that, okay, there is a store word with some address, okay? And then I see this load word, and I also put this load word with this with some address. And I said that if these two are the same, I can forward these things from each other, right? So far so good. But what if that I don't know the address when I'm actually decoding the instruction? For example, if you can look at this, R7 itself is dependent on this instruction, right? And this instruction is inside the pipeline. So by the time I'm decoding this instruction, I still don't know the value of R7, okay? I don't know the address, right? So what do I write into the LSQ? I don't know. This is R7. Whenever I know the value of R7, I put it there. And then same story for R1. R1 is dependent on the previous instruction, okay? And what address this R1 is this load gets depends on the value of R1. And now to make things even more complicated, let's say that this instruction can be issued way before these instructions, because there is no dependency for R1 and R2, but maybe there are dependency in R3 or R9. So in this case, how do we fix this problem, right? So should we stall? Should we not stall? Does anyone have any suggestions? First of all, is there anyone that didn't understand what the problem we have here? So there is a potential raw data hazard in this case. That is, I may or may not be able to issue the load before the store. If R1 and R7 are not equal to each other, I can definitely issue the load before the store. But if R1 and R7 are equal to each other, then I cannot issue the load before store. But value of R1 and R7 is also not known during the decode stage. And there might be also additional dependency that further delay knowing the address. So what should I do? Yeah. You can guess. And that's what we do. So this is, as I said, it's called memory disambiguation. Do I have the answer here? Oh, maybe not. So when we don't have the answer, we make a guess, okay? So this is called disambiguation speculation, okay? So you make a guess and say that, okay, I think R1 and R7 is not equal, or it is equal. You let the instruction to continue, but since you have your load store queue, once the addresses are actually known, you will realize whether you make a mistake or not. If you made a mistake, you flush it again and you redo the load or you redo the store, okay? If you didn't make a mistake, then great, you get performance boost, okay? So what you do is that you see that there is a potential dependency. What you would do is that you make a guess and you think you, for example, say that, okay, I assume that these are not the same. So you issue the load before store. You read the value, you continue. At some point, you will know the address of the store. You can check it in the LSQ to see whether these two values are the same. If they are the same, you made a mistake. So you flush everything from the load onward. So remember the coloring? You color all the instructions that use the value of load word. You squash them all from your pipeline and from the ROB and from the reservation session and everything. Okay? And then interestingly, you can have, to make this guess, same, all those stories that I told you from branch prediction, it also applies here. Okay? So for example, you can have a dynamic predictor, you can have always not taken predictor, you can have always taken predictor, you can update it with the history, you can use all of those tricks here as well. Okay? Yeah. Yeah, you can also stall, right? So whenever I see this and I see a load and I don't know the address, like the previous addresses are not resolved, then I'll wait. I wait until I know these addresses. So once I know this address and I know this address, then I continue. But problem is, I really want to issue my loads as soon as possible because loads are the most time-consuming instructions in the processor. So that's why you do all these tricks to even save few cycles for your load, you issue that. Any other questions? All right. So I'm going to finish the discussion of out of order execution with the real world example. This is the example of a design called Boom. So this is actually a RISC-V based processor that is available, open source design. It's also been taped out. Just wanted to show you that, all the things that you've learned and how they're connected. So as you can see, it has a front end, it has the execution or back end, and it has the load store unit. This is your cache. We still haven't talked about the cache and TLBs. So this part you still haven't you haven't understand yet. But these parts you know pretty well. So this is your instruction memory or instruction cache. Again, for now you don't understand what are these and why you have tags and TLB. But this is your initial part that you fetch the instructions. This particular one fetched 16 bytes at the same time. So it fetched 4 instructions at the same time. Okay. So as a result, you can fetch instructions. This is a 4 byte, so you can fetch 4 instructions at the same time. Then you put it into the fetch buffer. This is the register that you use between the fetch and decode. So you put this, it can get up to 34 entries. So this is the number of things that you can store there. Then you decode 4 wide as well. So you code 4 instructions at the same time. Okay. And here you also have your BTB, your branch predictor, your RAS, everything is also happens in the front end of your processor. Okay. Then you have your reorder buffer here. Okay. So you put things in your reorder buffer. It has 128 entries. Okay. Then you have your distributed scheduler. Remember I told you that you can either have one big reservation station or you can have per functional unit reservation station. This one has per functional unit, so it has one for integer, which has 32 entries. It has one for the memory, and it has one for floating point operations. Okay, so each one has 32 entries. All right. It also has a physical register for floating point and another physical register for integer. And each one is 128 registers. So this one is read after issue. Okay, so it's actually read things after the instruction is issued. Then you have, and it actually, as you can see, it has 8 different ports. So at any point, it can issue 8 instructions if it wants to the execution unit. Okay. And then look at the execution unit. You see that it has 3 ALUs. It has 2 floating point units. It has a branch. It has different things like multiplier, division, store, Roxy is an accelerator and all that. So there are different things that is happening in the execution units that they have. Okay. Then they have their store buffer and load queue. So it has 32 entries here and here. And then they can write things into their caches here. And this is the part that we're going to talk about later, like line fill buffer, MSHR, these things, you're going to see it later when we discuss L1 and L2. Okay, so this is their design of a allo order pipeline processor, which you hopefully can understand all part of it. This is also their kind of like a pipeline stage design. They have a fetch and decode and rename and dispatch, issue, read, execution, memory, and write back. Their fetch takes 4 cycles. Okay, the reason that it takes 4 cycles is that their branch prediction takes multiple cycles. Okay, so they actually read an instruction from the instruction queue. The branch predictor takes 3 cycles to actually do the logic. Okay, and then they put everything into this fetch buffer, as I said. Then they have their ROB, decode logic. Then they have the dispatch. As I said, they have the distributed issue queue. So the dispatch write things into separate issue queues. Then they actually read the instruction. This is read after issue. As you can see, it can read. So this numbers means I can read 6 registers and write 3 at the same time. For floating point, they can read 3 and write 2. And then this is fed into their execution units. As you can see, execution units are different things. So one is ALU, one is ALU and multiplier and divider and floating point and so on and so forth. And these goes back into the register files. Okay. They also have one specifically for the memory units, right? So they have the load store queues and caches and all that. And the write back stage is basically writing things back into the register. Any questions? Great. This is also their like the step-by-step design. Boom has 3 different versions. The one that I showed you is version 3. This is the latest version that they had. Previous versions were simpler designs. So again, 4 cycles for fetch. As you can see, the BTB has been looked at in these cycles. They also use a take branch predictor. Then they have a decode, a dispatch, then the queues, then issue, register read, execution, write back. And as I said, some of the executions might take multiple cycles, right? So for example, if you're reading from the memory, it might take 4 cycles. It might take even more cycles if you have some form of an accelerator. If the branch is basically detected here that we have a misprediction, there is a 12 cycle of miss penalty in this particular case. Yes. Yes, it takes four cycles to get one set of instructions. Yes. But then you read 4 of them, so you feed the pipeline very quickly. Any other questions? Yeah. Uh-huh.
They can be included for that, like, it's too dynamic.
What do you mean included in the prediction? Yeah. Yeah, well, you can, yes, you can know the type of instruction and say that, okay, this instruction takes 4 cycles, so I can wake up earlier and so on. Yes, you can. For memory, you can't, because for memory, you don't know whether it's going to be L1 or L2 or L3. But for regular instructions, for sure. Like if it's an add, you know. All right. All right, guys, let's have a quick break and then we come back and talk about something else. Okay. So we talked a lot about processors in order, out of order. So now we want to kind of move on from the processor for the time being. We're gonna again look at out of order execution for your CA3, and there I'm going to give you a little bit more materials for your CA and how to implement it, the specifics of that. You can also look at the Boom core documentations, and if you want to learn more about specifics of that, you can definitely do that. There's also nice open source documents about like Intel processor, AMD processors, if you're just generally interested. But now you have all the knowledge of understanding these things. Previous lecture was about like all these advanced topics that we talked about. It's important to kind of know a little bit of that, but of course, many of these things you will learn more about them when you actually use them in real world. Some of it you're going to see in CA3, some of it you're not going to see until you actually start doing some research or working in these companies and so on and so forth. But I wanted to give you kind of like, big overview of how things are happening in like out of order. Okay. But from this lecture forward, we're going to start talking about memory for a little bit. We're going to come back to the processors, and we're going to talk a little bit about multi-core processors as well. But that's mostly all the things that we wanted to talk about processors. We already covered them. Okay. So let's talk about the memory hierarchy. Remember that I told you that the model that we are going after is the store program model, or von Neumann model, where we assume that there is a processor, which inside the processor there's some form of a data path and controller, and there is a memory that is kind of interact with this CPU. And of course, there is an input and output to the system. So far, we kind of abstract away the memory and said that the memory is just this main matrix or block that you put the address and you get the data. We also assume that the memory is kind of sort of instant, that it takes one cycle regardless of the address that you put, you get the value that you want from the memory. The reality, of course, is that's not true. And in fact, CPU is significantly faster than memory. This actually leads into a big problem in design of CPU, which is called memory vault. Remember, I told you that we managed to build better transistors and make the transistors faster. As a result, CPU gets faster. Well, what happened is that over the years, so this is like, early 50s all the way to right now, CPU performance grows significantly faster than the memory. The reason is that the technology that we are using for memory is fundamentally different than the technology that we're using for the processor. And while the processors gets like 60% faster per year, unfortunately, memory gets only 7% faster per year. Okay. As a result, we are leading to the problem that regardless of how fast the processor gets, the overall end-to-end latency of the program not going to grow because you still need to fetch things from the memory. You need to bring things from the memory. And if the memory is slow, it's going to slow down everything else. If all you need to do in the processor side is just stall and stall and stall, then it doesn't matter how fast and how many lanes you have because you still need to wait for the data to be brought from the memory. Okay? And this is the problem that we don't need to just make the CPU fast. We also need to come up with new architectures, new ideas from the memory side to make both of them fast. Okay? And the reason that memories cannot get really fast is there is a fundamental challenge in memory design. That unfortunately, memories can either be fast or could be large. You cannot have a memory that is both large and fast. And the reason for it is just the technology that is using. You have seen this slide before. The fastest memory that we have are the flip-flops or registers. They are incredibly fast. They're as fast as the CPU. So you can actually access them within one cycle. And this is your register files or any sort of buffer that you want to have. But they're very expensive in terms of the number of transistors and the area they occupy. So I cannot have like a massive memory of registers and then kind of interact with it. My register file can only be 1 kilobytes at most. Okay, yes. Why 1 bit requires tens of transistors? This is kind of like a digital logic class. So essentially, you have to see how a flip-flop is kind of like being built. There's required multiple like CMOS and NMOS transistors to actually store 1 bit of a flip-flop. So you actually need to see the circuit of a flip-flop to see how you actually can store. So that's why you need multiple transistors. There is no known logic circuit that can store 1 bit of data with less transistors. And generally, the reason, like very intuitive reason for it is that in order to be fast, okay, you need current, okay? You need a lot of current to make things fast. In order to make a lot of current, you either need a lot of transistors or you need large transistors. That's why. Okay. But this is generally is because you go look at the design of the flip-flop, and you will see that how the flip-flop is designed, and that's why it needs tens of transistors. So M115C, I'm actually teaching that quarter, so welcome to take that class. So that's the structure of our registers, okay? Then you, if you want a little bit more storage, you go to the SRAM technology. And extra SRAM also requires 6 transistors, okay? So SRAM is like this very famous architecture that this one is actually connected to this one, and this one is connected to this one. And then you also have these 2 access transistors here. So this is one block of an SRAM. So this, in order to store 1 bit, this is what you use in an SRAM. Okay, so this is your so these are your two input and output to an SRAM transistor. Okay, so you need 6 registers for storing one bit, and then you also need lots of other analog circuits for reading and writing to an SRAM. So it's also very expensive. It's slightly slower than a flip-flop, but it's still slightly bigger than a flip-flop. Then you go to the next tier, which is the DRAM, dynamic RAM. Dynamic RAM is actually pretty nice in terms of storage. It's just literally one transistor that one of the pins are kind of like designed such that it has a capacitor. And essentially the way that you read it is you store the value in this capacitor. And then you can read zeros and ones from it. Okay. The problem with DRAM though is that although it's fairly dense, it's pretty slow because this capacitor is very small. And in order to read values, this capacitor basically needs to drive this line, and this line is very heavy in terms of capacitance. So it's kind of like think about like a tiny person tries to move a really large rock. It takes a lot of time for them to move it, right? So reading and writing from DRAM is significantly slower than reading and writing from a register file or an SRAM. But it's very, very compact, okay? So you can have gigabytes with one bit. Another problem with DRAM is reading and writing destroying this value, okay? So you need to refresh the DRAM after every time that you read and write. Not only that, there is also a leakage. So regardless of how you build this design, unfortunately, there's a tiny bit of leakage over time from the charges that are stored here. And as a result, even if you don't read and write from DRAM, you need to recharge it or refresh it. So DRAM require constant refreshing, usually tens of milliseconds required to refresh a DRAM cell. Versus the SRAM and flip-flops, you don't need that, okay? And finally, you have the disk technology. This technology in the past, it used to be hard drive, disk drive. Now it's like flash or NAND gates. These are very, very efficient in terms of area. So you can have terabytes of data because they use fundamentally different technology. They don't use transistors. They actually use phase change materials or other materials. But they are very cheap, very slow, very, very slow. It takes milliseconds to read bits from flash. Okay, so that's the problem with them. Okay, so in terms of the sizes and the access time, so register files are usually in order of kilobytes. You can read it below nanoseconds, so you can read it within one cycle. SRAM is tens or hundreds of kilobytes, typically range between 2 to 5 to 10 cycles, okay? DRAMs is gigabytes, but it takes thousands of cycles, so usually 1,000 cycles, so in order of hundreds of nanoseconds to read DRAM. And then disk is, you have it in order of terabytes, but it takes hundreds of thousands of cycles to read, okay? So that's the fundamental challenge that we have with memory, that we love this, but we also love this, right? So you need both. You need the speed of this guy, but you also need the storage of this, right? Because there are a lot of things that you want to store in your computers. You cannot like have a computer that only have kilobytes of data, but you also cannot afford to read the flash all the time. So what do? We use this notion of what we call memory hierarchy. So you create a hierarchy of these memories. You use all of them. You don't use just one of them. You use all of them. So you use a small memory that is close to the CPU. Use a bigger memory that is further away, and then another memory, and you can have many, many layers of this, okay? And you try to do this trick that if the majority of the time I talk to this memory, and somehow I can efficiently move data back and forth between these layers such that most of the time I have the data in this layer 1 memory, then I'm going to have best of both worlds, right? So I have the illusion that I have a memory that is large and a memory that is fast. So that's the ideal in the world of memory, that if somehow I can magically manage the data movement, that whenever the CPU wants it, I can provide it from the layer one, right? From the register file, for at least from the SRAM. If I can do that, then I'm not gonna never see the delays of a disk. Okay, so how do we do this? That's the story of the memory management and cache design that we're going to talk about in the rest of this lecture and next week and on Thursday. Okay. And you got a question? Memory one. So think about, for example, memory one as your register file. It's the first memory that you interact with them with. So as you have seen so far, register file is technically within the chip, right? So that could be your M1, or your M1 could be the first layer of SRAM. So why this would work? So the reason that this would work is there's a nice analogy in the book that I also use. Consider, like, a library, the problem of accessing data as problem of accessing books. Okay. So you have all the books in the world in the library, right? So for example, you have a Powell library, all the books are there, right? But anytime that you want to read a book, if you go to the Powell library, it's going to be very, very slow, right? So what do you do instead? You create a hierarchy, right? So you get some of the books, you either buy them or rent them, and you carry some of them in your bag. And furthermore, now that's like a midterm season, for example, you have an exam next week, the book that you're going to use, you probably put it on your desk, right? Or you're going to put it on on some form of a storage in your room. So you actually create this kind of hierarchy of data storage, that the ones that you use the most, you put it closest to you. The ones that you're going to use in near future, you probably put it somewhere in the room. The ones that you're going to use it in longer future, maybe you store it in the attic or somewhere else in the house. And the ones that you're not going to use it until many, many long time in future, they're going to be in the library. Right? And then if you need it, you have to drive to the library, or you have to walk to the library, get it, and come back, which takes a lot of time. Okay? Exact same idea happens in memory hierarchy. Okay? So essentially what we do is, and then of course, you might wonder that, okay, if I want to minimize this, why don't I put all the books in my desk? And the answer to that is you have limited space, right? Yes, ideally you wanted to have all the books that you ever needed always next to you, but the reality is that you have limited space in your bag, you have limited space in your room, and so on and so forth. So you cannot have all the books in the world in the same place. So again, same story happens in the memory, right? And then now consider the books as data. Same idea happens in the cache design. Okay. And this is, again, if you remember, we talked about this for branch and branch prediction. This is the same idea, that this is the principle of locality, that it's only a small portion of data you need at any given time. And you have two types of localities, right? You have temporal locality and spatial locality. Temporal locality means that if I need this book, I'm going to use this book again and again in near future. For example, until my midterm is finished, I'm going to use this book. So for some good amount of time, I'm going to use it. That's why you put it in your desk, because you're going to keep reading it. But at some point, you no longer need it and you can discard it. And then there's also spatial locality, which means that, for example, if you're taking computer architecture course, you want to have access to your book. Maybe you also print your slides. Maybe there's another relevant book. So you not only you read the reference book, but you also read the relevant books to that. So spatial locality is similar idea, that if I read data X, I'm probably going to access X plus 1 or X minus 1 or X plus 10 and so on and so forth. So data that are in address-wise near the same data that I read, I probably need those things as well. As a result of this, the idea of generally caching and memory hierarchy is that I try to maximize my temporal and spatial locality as much as I can. You might also wonder, what if I don't have any locality? What will happen then? Then you're not going to get very, great performance. So your performance is not going to be as great as you have lots of locality. So at some point you need to go and bring the data from the flash and so on and so forth. So it's not like you can always guarantee that you always have the best performance. Okay, so this is what we're going to do. We're trying to bring more frequently used data as close as possible to the CPU. And as I said, this is a hierarchy. So I have level 1, level 2, level 3, and so on and so forth in my design. Okay, this is typically what we have. So we have the CPU, we have our registers or register file closest to the CPU. Then we have what we call a cache design. This is the temporary that is closest to your system. Then you're going to have your main memory. This is your DRAM architecture here. And then you have your disk, and this is your flash or whatever your technology that you're using. And this would be usually SRAM. Okay. And this is your flip-flops. Okay. Within the cache, sometimes you can have a separate instruction cache and a separate data cache. The reason that you want to separate these two is that their locality is a little bit different. In instruction cache, you might use some instructions more often than not, versus data cache, the behavior might be very different. So you usually want to have a slightly different instruction behavior, like different ways of storing your instruction versus your data. That's why you separate the caches for instruction and data. Okay, at least when you're going to see later that inside the cache itself, we have multiple levels. Level 1 of the cache is usually separate between instruction and data. The second layer and third layer is usually combined. Okay. Any questions so far? Yes. Why can't we make the main memory out of SRAM? Because it will be small. So I want gigabytes of data in my main memory. Because, for example, I want to load the entire PDF, right? And I want to put it in my DRAM. I cannot load the entire PDF in my SRAM because it's small. Yeah. Same for like pictures or browsers or like an app that you open. Remember, like, have you seen like when you open an app, it takes a long and then it's like smooth after that? That's what's happening. It's loading it from the disk, put it in the main memory, and then bringing the pages that you need more into the cache. That's why like things are becoming so fast after a little bit. Okay. So this is the principle of caches. Okay. So usually we also, some people use the kind of symbol of $sign to show it's a cache. So just keep in mind that this is what we usually show. So in cache, there are two possibilities, right? So since cache doesn't have all of your data, right? Because all of your data is stored in flash. Like everything that you need in your computer that you ever use is going to be in your flash. It's not going to be in your main memory. It's not going to be in your cache. So in your main memory and your cache, there is a potential of not having that data that you want. When we don't have that data, it's called a miss. Okay, that means that the CPU requested that address, but that address is not available in the cache or in different level of cache or in the main memory. This is called a cache miss. Okay, if the data is there in the cache, we call it a cache hit. Later, I'm going to talk about how do we kind of check this, like the availability of the data. But obviously, since data is much smaller, you have a cache miss and a cache hit. Okay. So why cache is so important for the performance? And as I said before, so far we assume that this data memory was just one cycle, right? So we say that, oh, okay, one cycle fetch, one cycle decode, one cycle execute, one cycle memory, and so on and so forth. But this only means that we either read things from the flip-flops or from an SRAM that is very close, okay? But as I said, this only works if there is a cache hit in level 1. In most cases, It's not in level 1. It might be in level 2, in level 3, or it might be in DRAM, or even worse, it might be in flash. So we might have thousands and thousands of cycles of stalling if the data is not available there. And we haven't seen it yet in our designs because we always assume that things are available at the moment, like instant availability. Out of order is slightly better because in out of order, you can feed other things to the pipeline and so on, but still in out of order as well, if in one instruction requires thousands of cycles, then there will be many instructions that are dependent to that instruction. At some point, you will run out of the independent instructions. So the design of the cache has a significant impact on the performance of the overall system, because if the data is not available, you have to stall and wait for that data to come in order to execute the rest of the instructions, if they are dependent, of course. Okay? So what are we trying to do? We are trying to minimize this amount of stalling. We want, in ideal world, we want to have a system that we put the address and boom, we get our data. That's what we want to achieve in a cache design. Okay? How do we measure that? This is used by this formula called average access time to the memory. When I say memory, I mean everything, like, caches, main memory, and this. Okay? So usually the way this is measured is hit time plus miss rate times miss penalty. And this is usually measured for the first level of the cache. Okay? So let's say, for example, I have a memory hierarchy that only has one level of cache and one level of main memory. Okay? Like L1 cache. Okay? So the way this is computed is that if I have a CPU that requests the data, the average access time of providing a response to the CPU is the time it takes that I need to search the first level of cache. This is called hit time. Regardless of whether or not this value is in this cache, I need to search the cache. Okay? So either all the time the value is there and I can provide it. In that case, my miss rate is 0%, right? If every time that I request an access in L1, the data is there is no misses, right? So miss rate is 0. So average access time is just a hit time. That's the ideal world, right? Reality, though, is that there are many instances that you request something and the data is not in L1. As a result, I need to go to the next layer. This next layer is called miss penalty. The time it takes to bring the value from the lower level of memory to a higher level is called miss penalty. And the amount of time I need to go to a lower level is the miss rate. Okay? So for example, in most modern systems, miss rate is like in order of like 1 to 5%. Okay? Miss penalty is, let's say, as I said, for example, if I only have one level of cache, usually miss penalty is in order of thousands of cycles. Okay? And hit rate is usually 1 cycle. Okay? So you have a number like this, right? So if you have, let's say, 1% miss rate, you will have something like 1 plus, this would be 10, right? Yeah. And then, so 11 cycles would be your average access time, right? So even if you have only 1% miss rate with a memory that is 1,000 cycles slow versus 1 cycle, you're going to have 11 cycles. On average, this memory, average access time of this memory is 11 cycles. Okay? And then you can also write this formula this way, right? So you can also write this formula 1 minus miss rate times hit time plus miss rate times hit time plus miss time. These are the same. This results into the same thing, right? Because essentially what will happen is this, like this. So the times, like in your hit rate, or you can actually write this as hit rate. So the times that you have a hit, the amount of time that you need to spend is the hit time. The times that you have a miss is hit time plus the miss time, because you still need to search, right? So you still need to search the memory, but then you go to the miss as well. Okay, so just keep that in mind, that the way that we write this is easier to see. That hit time is always there. That's why it's very important to minimize your hit time. But then you also want to minimize your miss rate. You also want to minimize your miss penalty. You want to minimize all of them. Okay? Any questions here? Okay. So we want to minimize this average access time. What is the main challenge? The main challenge is that you have limited space, right? So how do we fix this issue? How to optimize this average access time? We introduce cache management in order to fix this, okay? So in order to understand how do we do the cache management, first let's actually see how do we store the data. So I'm going to give you a little bit of kind of like, data management, where do we store, what do we store, and things like that. And then I'm going to introduce 3 ways of designing the cache, called direct map cache, set associative cache, and fully associative cache. I'm going to show you the difference between them and the pros and cons of each one. Then we're going to go after optimizing that designs and showing you how do we improve the hit rate, how do we improve the miss rate, how do we improve the miss penalty, and so on and so forth. Okay? So in order to first understand how the cache works and how do we store data in the cache, you have to first look at how do we store the data. The input to the system would be the address. So always the input to the cache hierarchy system is the address. Addresses could be 32 bits, could be 8 bits, could be anything in between. Let's assume that addresses in our designs are 32-bit addresses, okay? What do we need is 2 things. First of all, we need to determine whether this data is available and does exist in the cache. Essentially, we need to decide whether this is a miss or a hit. And then the second thing is that if this is a hit, we need to also provide the data. So we need to provide the content. So there are 2 things that we need to do in designing the cache, okay? For a regular, for the entire memory space, if I have 32-bit values, okay, if my addresses are 32-bit values, I'm going to have 4 billion lines of memory in my design, okay? So this is the entire space that one program can access, okay? In reality, I'm not going to have 4 billion addresses in my design. What I would do is that there are 2 things. Later, we're going to talk about this thing called virtual addresses, that you provide these addresses as you wish, but then we're going to translate it into the addresses that we want. But for now, let's assume that my flash memory or my disk memory is as big as this 4 billion lines. So don't worry about it for now. Let's assume that any address that I provide, I eventually can go and grab it from the flash. But for the cache, I cannot have 4 billion lines, obviously, right? As I said, in my L1 or L2 cache, I have tens of kilobytes. I don't have billions of lines. I only have very, very small addresses, okay? So what should we do? We need to do some form of a mapping, right? So if the bottom one is my flash or my main memory that has all the possible addresses, what will happen is that some of these rows in my main memory are going to be mapped into the same row in my cache. For example, all of the gray ones going to be mapped into that cache address there. All the blue ones going to be mapped to that cache address there. How did I do that? For example, look at the addresses. So here, the simple example is that I just look at, let's say I have 8 different rows in my cache, okay? What I would do is that I just look at the lower 3 bits of the design, and based on that, I assign it to my cache. So simple addressing that if my address are 32 bits and I only have 8 entries in my cache, I just look at the lowest 3 bits and say that those that have the same lower 3 bits gonna be mapped into the same line in my cache. Yeah. Yeah, so this is your cache. So when this request from the CPU comes, you search the cache first. You see whether your data is there or not. If it's there, you provide that data. If not, you go to the lower level and do it. But what I'm saying is that since your memory is significantly larger, there are many requests that's not going to be in the cache. Yeah. And I also need to come up with the mapping, right? This is just one random mapping, right? So this is, I'm just saying that, okay, lowest 3 bits, that's how I'm gonna map the bigger memory to a smaller memory. But the question is that, is this the best type of mapping that we can have? Is there better things that we need to do? What sort of assumptions do we need to make in order to make this happen, and so on and so forth, okay? The second thing that we need to also know is that if 4 of these blue lines going to be mapped into that one blue line, how do we know which one did we store, right? So this one, if the address comes, right, and the address says 10101, I need to go to the cache and say that, okay, 10101, I look at this lower 3 bits and say that, okay, this is the one. But how do I know that this is actually this data and not this data or this data or this data, right? Because all of them map into the same address in my cache. In order to fix that issue, I'm going to use a tag, similar way that we use tags for BTB. I need to also store the tag, which is essentially tag says, is it this one, is it this one, is it this one, or is it this one? What do I store for the tag? I can store the entire address as the tag, right? So essentially I can store 11101 as the tag. And for example, if this one tag is this, then I compare the address and say that, oh, this tag doesn't match with my 10101 address. As a result, this is a cache miss, right? So the address comes 101010. I look at the first 3 bits. I go here, I check the tag and compare the tag with this value and see that these two doesn't match. I know that this is not the value that I stored. So I need to go to lower level and store that. An optimization similar to the previous time is that instead of storing the entire thing, you can also always just store these 2 bits, right? Since you already have the index, you can just store these 2 bits. So that's also another thing. You have seen this in the BTB design as well. But for now, what I'm trying to say is the following, that I provide an address. I need to have mapping of bigger memory to a smaller memory. So I need to come up with some good mapping. And the second thing I need to do is that I need to come up with some form of a tag store mechanism and a tag checking mechanism to compare these two to know whether these things are matched or not. Okay? That's where I'm going to pause, and then we're going to come back and finish this next time. Okay?